Thank you for this invitation and thank you for this nice introduction. Also, I would like to take the Cryptist, first Cryptist, all the members because of this nice event and inviting me to giving a talk here. I'm really appreciate this, especially this building and being together with these nice people all together. Yeah, I'm from Middlesex University. You know this university, but maybe you don't know about the Institute of Mathematics. So this institute was founded in 2002, and we mainly focus on mathematics from academical point of view and its applications. I mean, you don't understand maybe real application, but of course using mathematics in any kind of maybe technology or, for instance, in cryptography or financial tools or AI or scientific computing or actuarial sciences. We have 4 departments: cryptography department. This is one that I am the head of the department. Financial cryptography is of course also interested in this event, I think. And scientific computing mainly focused on differential equations and their applications, and most commonly maybe artificial intelligence or machine learning, I mean. Of course, the last one is actuarial sciences. All departments give, academical degrees, Master of Science, doctorate, and doctorate on integrated on BS. So this is a state university. You are all welcome to our university, and we would like to share. By the way, I don't have the pointer. Yeah, thank you. If you're interested any kind of thing about Middlesex University, Institute of Mathematics, and its departments, or your messages are welcome. Unfortunately, I didn't say my email here, but oguz@meteoedituyar or oğuzyayla@gmail.com. You can send me email. I would like to reply immediately. Today I'll talk about one of my recent study together with my master student Tegrit Fetu. She very recently, 1 week ago, she completed her Master of Science, and we studied on single secret direction, and we will only give only a portion multi-part computation based on, and I'll give how we solve accountability in SSLE protocol. So this is the just outline. So multi-part computation is just, as you know, cryptography is a toolbox, and in this toolbox we have lots of tools. How to make a computation of a function which has multiple inputs, and of course you want to compute it securely. I mean, inputs are secure, and results can be obtained on the secure inputs. So, for instance, you have inputs x1 up to xn, where you want to pick the highest, the maximum one, but you don't want to reveal xi's. How to find which one is the maximum? So this is a max function. F is a max function. How to find this one without using a trusted third party? Of course, if there is a trusted third party, you can submit all your inputs and he can choose to pick the maximum one. But of course, here we focus on without trusted third party. APC can be done over arithmetic circuit. Arithmetic means addition, multiplication, or scalar multiplication. Here, all xi's are private. For instance, you can share or private inputs to maybe n parties, let's say 100 parties, your 3 inputs. So over these shares, all parties, 100 parties, compute their own shares, and at the end they obtain x6 and x7, but without knowing even xi's. Okay, this arithmetic operation. Of course, Boolean can be done, AND, NAND, XOR, or it could be Boolean one. Boolean one is even easy because you are over, I mean, in arithmetic one you are modulo n. Let's say your numbers are less than n. Here, of course, 0 or 1. Of course, there is garbled circuit version of Boolean circuits. Two-party is very easy for here's garbled circuit one, but it is very detailed. Of course, I am not going to MPC here, MPC tool. But if you're interested, I will suggest you Bonet's book. You can go to Bonet's book or Nigel Smart's book. These are two nice books, I mean reference books. You can refer to those books in order to understand what the garbled circuit is and arithmetic circuits are, how you can do multi-part computation. So today I'll go with SSLE. This is single secret leader election. Maybe you can see here. It's a protocol where a group of users work together to randomly select a single leader, where only the chosen leader knows that she is the winner and can prove her leadership at the later time. Of course, here maybe I can say we have here maybe let's say 30 people here. So one of us needs to be selected as a leader, but of course we want to select only one leader each epoch. Let's say 10 minutes. We want to select only one leader, but of course the leader wants to keep herself secret until she reveals that I am the leader. Why? Why do you want to hide a secret leader? I mean, any kind of maybe motivation behind? I mean, hiding a leader, I mean, maybe altogether we can. Exactly, as it is exactly the case as maybe leader who's responsible of doing something very important for that epoch. So, in order to prevent him from doing his job, of course, the leader needs to be kept secret for a while of time until she reveals the identity. Of course, the proof. Then it will be. Of course, the setup, registration, election, verification, these are very common in cryptography. You set up the protocol, registration, election, verification. Yes, against denial of service, you can prevent that user, leader. It was first published in very nearly 2021. Of course, maybe the main motivation here in this community, there's a list of validators in any kind of proof of stake network. In those networks, you have many validators, maybe 1 million or maybe 10,000 or 1,000 or 100 validators. Of course, each validator are responsible selecting a leader for each epoch, and for this leader, needs to, do the block validation. The leader will be responsible for proposing the block, right? That's maybe the correct. It is very near. Very near problem. New problem. The most basic one. Even this wasn't included in the presentation, but I tried to include this one into the presentation. So the most basic one was proposed by Bonnet again. Again, Bonnet is always around here. Maybe in terms of crypto protocol, you can see him around a lot. So here only participants commit some KI value, secret value, by just embedding into the LGAMAL or the script algorithm mechanism, G to the R, G to the KIR. This is just hiding KR. But anybody can prove that I know the KI by just taking KI power to this one. If you obtain this one, this is the proof that you have the KI. But if you don't know the KI, you cannot find which power of this integer is, which power of this integer gives that one. It is the script algorithm problem. So each participant shuffle and re-randomize. When a new validator or new user enters into the system, he randomizes each input, this one with R prime. This is U, this is V. You take R prime power if you're a new user. And using a randomness R, random or any kind of randomness from the maybe any kind of maybe some randomness beacon, you pick a random R. So this R says that which index is chosen. So each party tries that whether mine is chosen or not. If I am the elected user, then I try my key I, whether it is the power of first element gives the second one, then I know that I am the elected user. So this is my proof. So after end of this epoch, I can reveal my leadership election by just revealing my key I. Here I need to reveal my key I. But if you can do this with zero-knowledge proof without revealing key I, this can be done by non-interactive zero-knowledge proofs, and this is even used now in Ethereum by using some proof of key I. Ethereum uses this kind of selection mechanism. So this is the, most maybe practical and easiest one, but using just simple cryptographic mechanism here. Any question here? If no, maybe let's go to maybe NPC-based one. Here, each user, can share a secret key with other parties. All users in parallel take their secret shares and use a function called oblivious select, which outputs a random secret share. Heterogeneous parties generate the secret. Let's see how we do it. So here we need a function, oblivious select. Have you ever heard oblivious transfer? Oblivious transfer? Yeah, very nice, oblivious transfer. Yeah, oblivious transfer is, I have two inputs on my two hands, x1, x2. You wanna select one of them, but you don't want me to learn which one you selected. And you don't want me to learn which one you selected, and I don't know which is selected by yourself. So this is oblivious select, and I'm holding x1 and x2, I don't know which one you selected, and you select one of them, but you don't know which the other one is. So oblivious selection. So this is oblivious select, sending by random bits, selecting CA or CB. By here you say if B is 0, CB is selected. If B is 1, as you see, CA is selected. So these are all brackets are shares. This P is globally known, but all the others are shares. What is this over 2? How to do it for maybe n inputs? Let's say n is 4 here. So you can choose first two one. You select C1 share, C1 prime. Let's say for the next two pair, you select C3 prime, and for C1 prime, C3 prime, you select one of them, and this let's call it, this is C bar. This is C bar is either this one or this one, right? Kind of shares. So let's see the framework. MPC-based single secret election. Here setup. First one state is null. Each user, or let's say in the validator, each validator registers by picking random key and taking its hash, left part, right part. 128 bits, 128 bits on the left, on the right. Left part is shared with all the other participants in the list. So each user has her own key I. Registration verify, each user can verify her key if in the correct list. This is just because each user registers and the list is incremented. At the end, of course, time comes to selection of the leader, and the list is appearing there. Of course, each user needs to verify that, yeah, this list is okay. My key is there, so I am in the list. So registration verify does this. Okay, each user. If this is not equal, returns 0, and the protocol starts again. So then election, the most important one, election, because now we need to select user, leader. Each CI is set as, this selection done by each participant. Each participant sets his key, left party's key, as the CI, and oblivious select is applied here for each user and chooses C bar. C bar is selected here, and this C bar is by each user comes together and KL is reconstructed, because this is threshold-based secret sharing, and threshold-based reconstruction is done here. KL bar is obtained here. Now, user can see whether KL bar is equal to her left part of key. If this is the case, gives the proof that my key is this one. So see my key, it is the left part is here, and you can verify my key, my key, taking its hash, left part, right part. You can check that state is equal to my right part. So this is just a proof. Proof is obtained by election, at the end of election, but this is done by only reconstruction. So as you see, at the end of the election, if the user doesn't reveal her key, so leader cannot be understood. Okay. So this is kind of we said this is accountability problem. If the leader doesn't do his job, we call withholding. This is a withholding attack. How to overcome this one? Of course, overcoming this one can be done by simply committing key in a time lock puzzle. If you can commit this one into a time lock puzzle, then it means that after a time t is passed, anybody in the validator list can obtain key I, can make the leader responsible, accountable for the block proposal. So this kind of non-interactive zero-knowledge proof can be added, and time commitment can be used here. Instead of revealing only left part, also time commitment can be done here. So it can include accountability. So very simple, and this was first proposed in 2024 for shuffle-based one, but MPC-based one can be done similarly. Okay, these are references, as I told you. First, it was proposed here, SSLE. So this is another one, multi-part-based one, MPC-based one, and Done's one, shuffle-based one, and Ethereum's one is based on this one, if I can say. So this is all for my presentation. Thank you for listening to me. So questions, we can, I have 2 minutes to take questions. Please, easy questions. Maybe I can remind you, maybe you are thinking about your question. I know you have some hard questions, but you don't want me to have some trouble to answer your questions, but I can try my best to answer your questions. Yeah.
So, for modular architectures, like where composability is important, like I heard someone else just say that MPC is suitable. So, can you talk a little bit more about it?
Composability?
Yes. In modular architectures.
Yeah. In terms of security or in terms of maybe implementation?
For privacy preserving.
Yeah, composability, and sometimes, as far as I know, universal composability term is very common now in security of some architectures, because you use some simple tools. For instance, MPC here. In the MPC, you use oblivious select. In oblivious select, you have secret sharing. So you say this is modular. You have some modules. So in terms of security, you need to give some. You need to give composable proofs. we call it universal composability. So if you can give proof of secret sharing, and you can use this proof in giving the proof of the overall system. This is universal composability. In terms of, I mean, implementation point of view, I can say you that, of course, each level need to be, I mean, implemented as efficient as possible and as secure as possible. Then you can use those modular primitives in the framework and obtain maybe some efficient implementation of the general framework. I mean, from even in security and in implementation, this kind of modular composability is important, as far as I know. But thank you for your question.
Can I ask a follow-up question?
If we have.
But we have a networking session, and I know that Oğuz is here for rest of the day as well, so you can just catch him on the call and ask your questions. Thank you. Thank you again. It was an amazing speech.